Welcome back. What I want to do in this video is I essentially want to work some pH problems. And what I'm going to try to do in the next few videos is really just expose you to a lot of different types of pH problems. Because we can have different titration type of problems. We can have Henderson-Hasselbalch problems. And the one I'm going to work in this video is going to be a Henderson-Hasselbalch problem. Okay. And one of the keys to where you know it's going to be a Henderson-Hasselbalch problem is when they give you a pH and they give you the pKa's. Okay, so in this problem, notice they give me a pH and they give me a group of pKa's, and specifically these are the pKa's for phosphate. Now, phosphate exists as a proton donating system, and to understand what that means, let's actually look at it. So the highest order phosphate in terms of the number of protons on it is phosphoric acid, right? And phosphoric acid can donate a proton, right? And it's in equilibrium with what we call diprotic phosphate, right? Or you could equally call that monobasic phosphate, right? And then that can be in equilibrium with another phosphate that is monoprotic phosphate, right? And we can also call that dibasic phosphate. And then, of course, that's in equilibrium with which we normally think of as phosphate as PO4 3-. And so each one of these pKa's that I have listed here corresponds to one of these equilibrium reactions. And that's something important to understand. The pKa does not correspond to a particular molecule. It corresponds to an equilibrium of two molecules. So, for instance, pKa1, which is 2.14, corresponds to this equilibrium. Pka2 7.2 corresponds to this one, and then the third pKa corresponds to this one. And what we have to keep in mind is that the lower the pKa is, the higher the Ka is, right? So this pKa is the lowest, so that means it has the highest Ka, right? Because pKa is the negative log of the Ka. And so the higher the Ka is, the stronger the acid. Or we could equally say the lower the pKa is, the stronger the acid. And certainly phosphoric acid is stronger than any other acid here. And of course, phosphate is not an acid at all. Okay, so having said that, how do we know this is a Henderson-Hasselbalch problem? Well, typically you know it's a Henderson-Hasselbalch problem when they give you the pH and they give you a set of pKa's, right? Now, they ask us to find the concentration of diprotic phosphate. So they ask us to find the concentration of diprotic phosphate, and they tell us that the total phosphate concentration in solution is 3 millimolar. Now what I'm going to do is I'm going to come down here and I'm going to write the Henderson-Hasselbalch equation, and this is something that you should get to know very well. It's essentially equal to the pH that we're dealing with, which is equal to the pKa, and we're going to find out it's going to be one of these pKa's that we have listed here. So pH equals pKa plus the log base 10 of the concentration of the base in the equilibrium reaction over the acid in the equilibrium reaction. Okay, so there are several things we have to look at. Number one, they don't give us any concentrations of any of the individual phosphates, so that doesn't help us, right? But we do know the total concentration of all the phosphates combined, and that's the 3 millimolar. Now, what you have to understand is the pH is at pH 7, right? It's pH 7. And what we have to do is we have to figure out which pKa we're dealing with, right? And so the pKa that we're dealing with is going to be the pKa2, right? Because if we're at pH 7, it's very unlikely that we're going to have this phosphate, right? And it's very unlikely that we're going to have phosphoric acid, right? The two most predominant species at pH 7, let me do this in purple, are going to be diprotic phosphate and monoprotic phosphate. Those are going to be the two most predominant species because the pH that we're dealing with is closest to that pKa. For example, if we were dealing with instead pH 2.2, then we would be dealing with pKa1. If we were dealing with pH, say 13, we would be dealing with pKa3, and that's simply because pH 13 is closest to the pKa3. So we're at pH 7, so pKa2 is the closest. So those two species that are around Pka2 are going to be the most predominant species, diprotic phosphate and monoprotic phosphate. So what we also have to realize is something else that we run into in this kind of problem is that since diprotic and monoprotic phosphate are the most predominant species, all the other ones, their concentrations are going to be so minuscule that we can essentially ignore them. So they're going to be so small that they're not going to contribute really at all to the total concentration. So that gives us something called the mass balance equation. The mass balance. And essentially what that is we can take the total concentration in solution, and that's 3 millimolar, right? And we can have that equal to the sum of the individual species in here. And I'm going to abbreviate this as A and B, and A, of course, is for the acid. So this would be the acid, right? And this would be the more basic species. So the 3 millimolar is going to be equal to the concentration of the acid plus the concentration of the base, right? And effectively, we can ignore the concentrations of the other species because they're going to be so minuscule that they won't contribute at all. Now, in reality, you are going to have a very small concentration of phosphate, and you're going to have a very small concentration of phosphoric acid, but in reality, the concentration is so small that they're not going to contribute at all. Okay, so we can effectively just use concentrations of diprotic, which is A, and monoprotic phosphate, which is B. Okay, but the problem is they don't give us either one of these concentrations. They're just unknowns, right? They're just unknowns. Okay, so actually, let me do this. Let me come over here. Actually, let me cut this out right here. Let me cut that out, fill it in. And actually, let me use the nomenclature that I did over here. So get my brush. And so this is going to be concentration of the base over the concentration of the acid, right? So I'm just using the same nomenclature I used over there on the right side. So just so we're in the same picture, right? Now let's go ahead and filling in what we know, right? Let's fill in. So the pH we're dealing with is pH 7, right? Which pKa am I using? Well, I'm using pKa2 because at pH 7, those two species in that particular equilibrium reaction are the most predominant species. So it's going to be 7.2, right? And plus the log of B over A. But here's the problem. If I just did log of B over A, I'd get a system with two unknowns, right? But the good thing is I have two equations. So I have a system of two equations and two unknowns. So what I can essentially do is I can solve for one of the unknowns and get it in terms of the other unknown, right? So what if I was to do this? What if I was to subtract A, concentration of A from both sides? Well, I would get the concentration of B, right? So I would get 3 millimolar minus the concentration of A, right, is equal to the concentration of B, right? So now I have concentration of B in terms of concentration of A, right? So if I was to take this B, right, if I was to take this B and I was to plug it in here, I would essentially eliminate concentration of B from the overall equation, right? And I could just solve for concentration of A. And that's exactly what I'm going to do. That's exactly what I'm going to do. So I'm going to plug that in, right? I'm going to plug it in. And so I'm going to get log of, and essentially on the top it's going to be, I'm going to do 3 millimolars, right? 3 millimolars minus the concentration of A, right? And that's going to be over the concentration of A, right? It's going to be over the concentration of A. Okay? So I hope this makes sense. Now I'm going to subtract 7.2 from both sides, and you'll see why I'm doing this in a minute. So if I subtract 7.2, I'm going to get negative 0.2 on this side. And if you get a negative sign, that's perfectly normal. And you'll actually always get a negative sign if the pH is lower than the pKa. And actually, while we're doing this, it's actually a good idea at this point to predict which one of these species is going to be higher. And this is something actually you should always do when you're doing these Henderson-Hasselbalch problems, is try to predict which species is going to be higher, right? So the pH is lower than the pKa. So if the pH is lower, we should expect there to be more acid, right? So the pH is lower than the pKa, so we should expect more acid, okay? And so that means that the concentration of A down here, which stands for acid, should be higher than the concentration of B. So what I get is I get the log of, and of course this is all in parentheses, right? I get the log of 3 millimolars minus the concentration of A is over the concentration of A, and of course that's equal to negative 0.2. Now what you have to understand is this is log base 10, right? So if I want to undo a logarithm, I essentially raise it to the power of whatever this base is, right? So if I want to undo this logarithm, I'm essentially going to raise everything, I'm going to take 10 to the power of everything, right? So I'm going to take 10 to all this business, right? And essentially the 10 down here, this base is going to eliminate the logarithm, and so that's going to leave me, at least on the right side, it's going to leave me 3 millimolars, right, minus the concentration of A over the concentration of A, right? But now what I have to do is I have to figure out what 10 to the negative 0.2 is. So let me bring my calculator out. So 0.2, let's see, negative 10 to that power. So it's approximately 0.631. So it's about 0.631, okay? And now I essentially want to get all the A's on one side, right? I want to get all the A's on one side, so I'm going to, let me come over here, I'm going to multiply both sides by point A to get rid of this denominator. So I'm going to get 0.631 times A is equal to 3 millimolars minus the concentration of A, right? And then coming up here, I can add concentration of A to both sides, and so I get 1.631 times the concentration of A is equal to 3 millimolars, right? Equal to 3 millimolars. And then I can divide both sides by 1.631. So that means that the concentration of the acid, let me come over here. So let me clear this. I get 3 divided by 1.631, and that is going to be about 1.84. So let me do 1.84. So the concentration of A is equal to 1.84 millimolars, right? And I think we should take this time to make sure it makes sense, right? The total concentration of A has to be equal, or it has to be, less than the total concentration of solution, and it certainly is. And let's think about this. Or actually, first, let's actually solve for concentration of the base, right? And remember, we expected the acid concentration to be higher, right? So if I take 3, the total concentration, and subtract it from 1.84, I'm going to get 1.16 millimolar. And so certainly the concentration of acid is higher than the concentration of the base, right? And that's exactly what we expected, right? The pH that we're at is lower than the pKa. And so if the pH, say, had been 7.4, we would have expected there to be more base, right? More base. Okay, and actually the concentration of acid, we can go ahead and convert that back, and that's going to be, let me erase that, that's going to be equal to the concentration of diprotic phosphate, and that's exactly what they asked us to solve for. Okay, so this is just one of the types of problems they can throw at you, and typically what's going to happen is if they give you a pH and they give you a pKa, you're going to have to write this thing right here, and this equation right here has a special name, and I mentioned it. It's called the mass balance equation. This is the mass balance equation. And whenever they give you a pH and a pKa, this is what they expect you to do. And if you take analytical chemistry, you'll get lots of practice and stuff like this. And essentially what you're going to do is you're going to eliminate one of the variables from the equation. So you solve for one of them and then plug it in terms of the other variable into the Henderson-Hasselbalch equation. And one thing that's good to do is to know exactly what it is you're solving for. In this case, we were solving for the acid concentration, right? So I wanted to get this Henderson-Hasselbalch equation in terms of the acid. If, for instance, they asked us to solve for monoprotic phosphate, I could have rearranged it to solve for concentration of A. And so my equation here would have been in terms of concentration of B, and that would have gotten me the concentration of monoprotic, the concentration of monoprotic phosphate. So I hope this video helped, and we'll do another one like this in the next video. And what we'll do is we'll actually look at a very similar problem. In fact, we'll still use phosphate, but we'll actually use a different pKa. See you soon.